Hello, my name is James Ware, and I will be talking about a carbon nanotube strain sensor for structural health monitoring by all these lovely people. This is a brief outline of the topics that will be covered. In the introduction, I will talk about the qualities that carbon nanotubes possess and what makes them desirable in structural health monitoring. Moving to the background, I will cover on traditional designs for CNTs and how they apply to structural health monitoring, what they have to offer, and how they come up short. Transitioning to techniques, I will go over the samples that were produced by this group for the experimentation and the various tests and calculations that were performed on those samples. In the results section, I will cover what the team found after their experiments and the further applications that were shown to be possible. In the conclusion, I will go over the closing thoughts and considerations for future experiments with CNT composites. For those of you who are unfamiliar with carbon nanotubes, they are, in their ideal form, comprised of a carbon hexagonal lattice. They possess an impressive resume of mechanical properties, including elasticity, the ability to deform to great lengths and then return to their original size and shape, piezoresistivity. When they undergo strain, their internal resistance to current varies greatly. They can also be arranged into large surface areas with even distribution, imbuing their characteristics onto large structures. They have great tensile strength, practically an engineer's dream, as they are almost impossible to break in tension. These qualities work in tandem to make them into inherent sensors. In the paper, the method of measuring their internal electric characteristics as they deform will be used to indirectly measure their deformation. CNTs are not without their issues, however. They are brittle and prone to fracture under non-tensile stress. They do not align on their own and require a material to mesh into, and a high concentration and even dispersion is needed for their talents to truly show themselves. This paper broaches the idea of creating a CNT composite that is flexible enough to undergo great strain while also still maintaining a high enough concentration of CNTs for their inclusion to be worthwhile. CNTs are used in structural health monitoring already, but mostly in research atmospheres. One of the methods is lithography, when the material having its internal strain monitored is sandwiched between layers of CNTs. The disadvantage here is that the method is very hands-on and requires a large and expensive signal array to maintain. Bucky paper is another material that is used for this purpose. It is essentially a sheet of forcibly aligned CNTs with no mesh, meaning that many of the flaws in CNTs are not compensated for and they remain brittle and ineffective outside of niche circumstances. CNT composites have been tested for structural health monitoring in the past, but they have yet to reach their full potential or widespread adoption. These composites could be cheap, versatile, and be very easily attached to existing structures if the right method and configuration was discovered, which is what this paper sets out to do. It wants to create a CNT composite with CNTs as the matrix and a polymer as the reinforcement. The two types of CNTs were created in this paper were a control Bucky paper for comparison purposes and a CNT composite. Bucky paper is fabricated by essentially hand mixing or sonicating lots of CNTs into a solvent and then evaporating the solvent away, leaving a thin film of concentrated CNTs. The unique CNT composite that was created by this group for this paper utilized different concentrations of CNTs as a matrix and had reinforcement polymer with a name I won't even try to pronounce, shortened to PMMA. This was done by mixing the solution of the two with a drill and curing multiple times until the composite was in a stable, dry state. This is a brief overview of the tests done in this paper. They performed EIS testing on both types of samples to determine their electric characteristics for simulation. They stuck the samples to a cantilever beam and performed static strain tests. They then performed a similar dynamic strain test, only now they vibrated the cantilever beam. And they simulated the dynamic strain tests using their EIS results, and they applied a neuron sensor grid to a vibrating aluminum beam. EIS stands for Electrochemical Impedance Spectroscopy. They tested their segments of Bucky paper and squares of CNT composites. EIS testing is done by fashioning a cell out of CNT material as a working electrode, a PT plate counter electrode, and a reference electrode. The cell is then has a variable AC potential fixed and a fixed DC potential applied to it, and its characteristics were recorded. These results were then used to create an equivalent circuit for later stimulation. Later, simulation. These are equations they use to determine these electric characteristics. I won't go too in depth on these because it will make more sense later when we cover the results of the EIS testing. They essentially calculate equivalent component values for the sensors if they were to be put into a circuit. The next test performed was the static strain test. Bucky paper and CNT composite sensors were adhered to a cantilever fiberglass beam and vacuum bonded to reduce slippage. These samples were then wired to a silver epoxy and a load was applied to the free end of the beam. When the beam reached maximum deflection, the internal resistance of the sensors was recorded. These are the beam theory equations used to calculate the actual deflection for verification. These should be very familiar to anybody that's taken solid mechanics, as they're pretty much standard in any questions that ask about cantilever beams. They then performed resistance calculations to convert their resistance values into strain values. These tests were done 5 times for each of the two different types of samples. The equation on the right, gauge factor, describes the sensitivity of the sensor, while the equation on the left describes normalized resistance. The test performed next was a dynamic strain test. This test was much the same as the static strain test from before, but with more elaborate equipment to record the variable responses from the sensors. This time, after the maximum load was applied to the free end of the beam, it was released and allowed to vibrate freely as results were recorded. A laser displacement sensor was used to measure the actual displacement for verification. The next test performed was a simulation of the dynamic strain test with a Wheatstone bridge assembly. The EIS values were used in calculations here to see if the sensors acted predictably enough to be designed with different types of work environments in mind. These were the equations used for the dynamic strain simulation to convert the resistance values of the sensors into voltages for the Wheatstone bridge. The last test performed was a neuron sensor grid. This experiment could yield the farthest reaching application, as a neuron sensor grid is essentially an array of sensors that can be broadly adhered to existing broad surfaces like bridges, cars, and planes. A particularized version of the composite was sprayed on an aluminum cantilever beam and sealed with insulation. A current was then run through the beam to detect resistivity on the neuron grid. Finally, the beam was dynamically stimulated with a load at its free end and released to vibrate freely. In the second trial, a small perforation was inflicted on the beam to see if the array could detect not only the vibration, but also the fracture. Moving on to results, these are the graphs yielded by the EIS analysis. This data was used in the simulation test. These are some of the graphs used for resistance calculation. Average values were used across the trials to curve fitting was used to produce a usable trend. This is the Randall circuit that was featured earlier. In EIS testing, the sensors were converted into these components, these equivalent components if they were to be put into this circuit: a polarization resistor, a double layer capacitor, and a Warburg coefficient. The polarization resistor value would indicate how well the sensor would resist fatigue and corrosion. The double layer capacitor would indicate the ability of the sensor to withstand charge and give a more reliable reading. And the Warburg coefficient did not end up being consequential in their calculations. These were the resistance measurements from the static strain portion of the experiments. While Bucky paper was more sensitive, it could not withstand the microstrain above 500 before fracturing, as it was very brittle. The CNT composite showed decent sensitivity, but most importantly, it exhibited a linear strain response with load, making it more reliable. These are the strain responses from the sensors. As you can see, the Bucky paper entered inelastic deformation before 500 microstrain. You can see the yield curve there. The linear strain behavior is illustrated here by the CNT composite, and as the CNT concentration went up, less strain variation was detected. These are the resistance measurements from the dynamic strain test. While the Bucky paper was way off the mark, the CNT composite mostly agreed with the real strain recording. This shows that the CNT composites can be used to detect deformation in a moving body quite accurately and reliably. These are the results from the simulated dynamic strain test for the CNT composite. While there is some error, it's explainable by minor factors that could likely be produced better with future iterations. The similarity shown between the real sensors recordings and the simulated recordings shows that the CNT composites can be customized before construction to produce better results with specific environments in mind. These are the results from the neuron grid experiment. A CNT composite of 10% concentration CNTs was tested in this experiment. The figure on the left displays the readings for the displacement, while the right displays the resistivity of the damaged aluminum bar. Again, the composite is remarkably accurate in replicating the vibration of the aluminum bar. There is also a detectable and predictable change in resistivity with the fractured bar, showing that the neuron grid can reliably dictate when there is a fracture in its structure. Finally, in the conclusion, these experiments in this paper show that the CNT composites can detect not only deformation, but impurities in their assigned structures. Bucky paper was shown to only be effective in narrow applications, proving that with enough research and implementation, CNT composites will be superior and the most popular alternate method. The characteristics of the sensors could also be predicted and therefore designed for specific circumstances. CNT composites with future experiments have great effects on structure and could even have applications in skin-adhered sensors. Thank you for your time.